Hi, everyone. Today we're going to be talking about linear regression. And we're going to be talking about fitting a line to data, sample variability of a regression line, hypothesis testing with linear regression, our implementation of linear regression, and model conditions. Seems like a lot of stuff, but these will be a brief set of videos. Content from these slides are coming from Montana State Introductory Statistics with our textbook. So let's begin with the example here from the textbook regarding a hypothetical population of chain sandwich stores. So this is the full population of all the chain sandwich stores of concern. So we have a amount spent on advertising in thousands of dollars in the x-axis, and then the revenue in the thousands of dollars. So each dot is a store, and this is the amount they spent on advertising. So let's get maybe an easier one. What is that one? It's well, it's kind of let's just get this one here. So this is $1,000 spent on advertising leads to about $15,000 in revenue, and for that particular store. And we can create this line. We can fit a line to the data by minimizing the distance between each point and the line. So we can find a line that minimizes the difference of all the points in the data to the line. And this process is called least squares regression. And we've talked about that. So in the equation of a line, we have a few components. Usually the computer algorithm will find you the best line that minimizes the distance between the points and the line via this least square methods. And either way, whatever line we have, we can have an equation of a line as we have seen here before. So the y-axis or the y variable is the outcome variable. We have one item here. This is the y-intercept. And here's the outcome or response variable or dependent variable. The beta, this is the slope of the line. The slope of the line, x is whatever the x value is. And then we also have the error term, which we won't really talk much about in this class, but it helps us identify the unexplained variation that not really captured by the line itself. So let's just focus on these other three terms though: the y, the outcome variable, the y-intercept, the slope, and then just the x value. So once we identify a line, we can identify the slope of the line, and then we actually get an equation. So for this equation here, for these data points, we have the y-intercept of 11.23, and we have the slope as 4.8. So we have our regression equation, essentially. And what this says is that if advertising is 0, then 0 times 4.8 is 0, and the expected revenue will be 11.23. Now, you can think of it as in thousands or not. So let's just think of it in the numbers here, and then you can change to thousands so things more consistent. So if your advertising is $0, you get 11 in revenue, 11.23 in revenue. Now, what happens if your advertising is $1? Well, if it's $1, you get 11.23 plus 1 times 4.8. So you get in revenue 16.03 in revenue, right? So, and that's just kind of following the line because we identify that slope. This is the key point here. Well, and the y-intercept as well. So when x is 0, what is the value of, what is going to be the value of the expected revenue? And then so on and so on. And that's kind of the beautiful thing about the equation and the variables that we can identify, well, what if we spend $6,000 in advertising? Well, then put 6 here, 6 times 0.4.8 plus 11.23, and then you get that result. Now, that we can do that more confidently if we have the full population of data, and you can actually expect kind of a general trend. Okay, it does look like there is a general linear trend here. The more we advertise, the more we spend on advertisement, the more revenue we get. But let's recall that usually we're working with sample data. And if we only have maybe 20 stores, information from 20 stores or a few selected stores, we may get one line. We can still generate that least squares regression line, and then we'll get a certain y-intercept and a certain slope. But if we have a different sample, we may actually get a different line, right? And then if you kind of put them together, you see, wait, that's not the same line from the two different samples, which may have some overlapping or not data in those samples. So, well, what happens if you keep sampling and sampling and sampling? Well, if you keep sampling and sampling and sampling, you will notice that you have multiple different lines. And it's kind of interesting too, because they will start getting farther apart at the end of at the end outside of the mean. And that's because it becomes more difficult to predict values that are farther apart from the center. And I think, as we have seen in the R implementation, you can actually get an idea of this variability here when you actually plot the best fitting line. But if we have the full population, we can see that the best fitting line to all those sample variability would be the one that we were originally identified. And we can actually create a histogram of the distribution of those slope values, and it should look normal, slightly, at least slightly normal. So that's kind of another interesting thing about statistics. But let's recall that with a real study, usually we only have one sample, so we're not able to visualize this variability. We just have one sample, so we don't really know the total variability. However, we can make assumptions about the distribution of the slope values to make inference about our sample, as we have done before. So because we are assuming that the sample variability is going to follow this normal distribution, we can make those assumptions about the variability of the slope. And we're kind of going to just go back to the same idea we have seen before about sample variability and the normal distribution and the assumptions we can make when testing for a particular value. So next, we're going to talk about hypothesis testing with linear regression.